Hello everyone, welcome back to the lectures in Introduction to Multi-Agent Systems. This will be the final lecture of the course, and in today's lecture we'll see the tools that we have discussed so far pertaining to multi-agent systems and nonlinear dynamical systems. How can we use those tools to actually develop distributed guidance laws for practical applications like for formation control problems, for rendezvous problems. We'll also discuss topics on cyber-physical systems and opinion dynamics, and also about coupled oscillators. In all of these examples, we will use the tools that we have discussed, and we will see how can we go about achieving desired behaviors in these systems. So let's get started. The first class of applications that we focus on is that of a formation control problem. Before we get into how to solve a formation control problem, we must remember that when we are given with a multi-agent system, then the agents which constitute the system can have various kinds of kinematics. Some of the kinematic models that we have discussed before are single integrators, double integrators, or the unicycle model. In today's example of the formation control problem that we are going to discuss, we'll consider the simple unicycle model. So what does the unicycle model represent? As the name suggests, it represents a single wheel and the corresponding point mass model that we get using this wheel. So let's specify our conditions for the underlying framework. Consider a group of n unicycles the kinematics of the ith unicycle is given by xi dot is equal to vi cos of alpha I, yi dot is equal to vi sine of alpha I, and alpha I dot is equal to some omega I, which is oftentimes the input to the system. But let's talk more about this slightly later. So why the unicycle model? Why are we going to look at it? Because let's write the motivation for using this model. The major motivation is that the point mass unicycle can serve as a simplified representation of various real-world systems. Some examples would be a car, a fixed-wing aircraft, a submarine, etc. So let us understand the kinematics a bit better. That will help us understand how it serves as a simplified representation. Let this be our ith unicycle. Then its position coordinates are given by xi and yi, and the unicycle has a heading angle alpha I, and its velocity or its speed is given by vi. Okay. The rate at which xi, yi, and alpha I evolve over time is what is given by the kinematic model. So the unicycle system is in fact can be used to represent any system which basically has a heading direction and can turn left or right and move with a certain forward speed. That is precisely the reason why a car, a fixed wing aircraft, a submarine, a bus, a missile, and many other systems like this can actually be represented using a unicycle system. So this is the reason why we are looking at the unicycle. I'll add one more point here. Notice that for the unicycle system, let's look at this bigger system, which is North Point Mars. So we can add some pedals here. The person who's riding the unicycle can actually move the unicycle in two ways. First is a person can turn the handle, which will actually cause the heading angle to change. And the second is the rider can pedal such that it can control the speed at which the wheel is moving. Hence, there are two inputs to the system: the forward speed and the angular speed. These are the two different inputs. Again, there are three states which describe the kinematic model: xi, yi, and alpha I, but there are only two inputs, vi and omega I. Precisely because of this is an under-actuated system. Okay, so what we are going to do is, while it is an under-actuated system, it is a bit difficult to control, but still, since it is representative of various real-world systems, we are going to consider that our agents in the multi-agent system have a unicycle model. With this, our objective is as follows. Our objective is, so remember that any wheeled robot which can move ahead, other than the caster wheels, we are not considering them. So anything that is not omnidirectional, but is rather constrained with something that's known as a non-holonomic constraint. So in the case of the unicycle, the non-holonomic constraints occurs because laterally it cannot translate. So any kind of a vehicle which cannot translate laterally and has a forward speed and can also turn left or right, they can be represented using a unicycle model. So we'll now assume that our agents are simply robots which are represented using the unicycle system. Then we say that we have n unicycle robots. We want the robots to achieve a desired inter-robot formation such that with desired spacings. So we simply say that xi minus xi minus xj should tend towards, this is basically the x separation between the two agents. This must tend towards some desired value given by dij x, and similarly yi minus yij, we can write one combined equation. Yi minus yij must also approach some desired distance. And this must hold for every pair I comma j such that they share an edge in the graph. So this dij is nothing but the desired displacement of agent I relative to, or let's write robot I relative to robot J. How do we go about solving it? For that, we quickly define some error terms, and using the error terms, we will construct a Lyapunov function. The error terms are the first one is the error along the x direction given by EIX is I summed over all of the neighbors of I, xi minus xj minus dijx. So this is nothing but whatever is the actual distance or displacement between xi minus xj and what is the desired value. So this is the error along the x direction. Similarly, we can write it for the y direction as well. Let's write it for the y direction. So EIY is nothing but yi minus yj and dijy. So these are the errors in the direction, in the x and y directions. So with this, let us now define the state vector. The state vector is equal to some p. P is a column vector given by x1, y1, x2, y2, up to xn, yn transpose. It's a 2n cross 1 column vector. Using this state vector, we can now define the error term as, so here we wrote the error term for every agent I, and every agent I has two errors associated with it, the error along x and the error along y. If you want to write it concisely for the entire system, then we have to use this error vector, the state vector. So I would ask the students to pause the video here and see if they can now write some error term E, which is a 2n cross 1 vector, such that it gives us all of the errors the errors for all of the agents in the network. I hope you've tried it. So the solution to this is equal to this. Let us highlight it in a different color. E 2n cross 1 is actually equal to the Laplacian Kronecker product I2 multiplied by the term P minus B. So if you have to write, the meaning of a Kronecker product is quite simple. If there are two matrices, let's say A Kronecker product B, and A takes the following form. Then it is simply equal to A11 times B, A12 times B, A21 times B, and A22 times B. So this is a Kronecker product. And the term B here, it is nothing but the desired displacement or the desired formation offset distances. So now, if we want the multi-agent system to achieve consensus, it is equivalent to saying that we want this error term E to go to 0. So this is a new control objective. So now what we can easily do is we can design a Lyapunov function, and we can say that its derivative is negative definite or perhaps negative semi-definite close to the origin or close to the equilibrium point. But since we want the error to go to 0, again, our origin is a desired equilibrium point. So how would we define the Lyapunov function? For that, we'll change these errors very slightly and express them along the body frame of each agent. So let's write the errors or the local body frame errors for robot I. This is very simply equal to this. E, let's say I1, E, I2. Again, there are two error terms associated with each agent as before. But now, instead of being along the X and Y axis, we want these errors to be along two directions. First is, let's draw the same figure that we drew before. This is our alpha I, this is bi, and this is xi comma yi. Okay. Ex and ey are simply along the X and Y axis. But it would make more sense if we can visualize the error in terms of the robot's body frame. Meaning, can we have the errors expressed along the V direction and along its orthogonal direction? Why is it easier? Because we have two control inputs. First is along V, and the second is along the lateral axis, which is the angular acceleration. Hence, it gets easier if we can specify the errors as well along these directions. So we'll specify the errors along these two directions. It is given by this. The errors have to be rotated slightly cos alpha I, sin alpha I minus sin alpha I, and cos of alpha I again. And this gets multiplied by EI along the x direction, EI along the y direction. So these are our new error coordinates, where E1 is simply the error along this direction, EI1, and the error along the lateral direction is this, EI2. These are the new directions of the errors. In the end, we also want, let's say, for example, we also want all of the robots to look at their neighboring robots or look towards them. Then, in order to implement that, we could introduce an error term in the angles as well. And we'll call it phi I, which is equal to alpha I minus alpha desired I, where alpha desired I is nothing but tan inverse EI y divided by EI x. Okay. Now we define a distributed, or we can design a distributed control law now using all of these three errors, which is given by this. The distributed control law for the ith agent is given by, let's write it, for the robot I whose inputs are Vi and omega I, we say that Vi, which is the speed component or the longitudinal speed or the forward speed, is some constant K1 times the error along that direction, along Vi. And omega I is simply K2 times phi I plus K3 times the error along that direction. So this is a very, very simple control law, which is derived using the three error terms that we discussed here. How do we know whether this control law works or not? Before we move on, let me quickly add that we want, or we choose, all of these parameters to be greater than 0. In order to show that this actually works, we will now propose a Lyapunov-based proof, or present a Lyapunov-based proof. So the Lyapunov function can now be chosen as V. Let's write it this way. V is equal to half times this summation, I going from 1 to n, where n is the total number of robots, times EI1 squared, the first error, EI2 squared, and phi I squared. Again, this is a very, very simple Lyapunov function, which is nothing but the sum of squares of all of the errors. And we can show very easily that V is positive definite. Positive definite. But the more important question is V dot negative definite? Let's see. V dot is simply equal to, we just take a derivative of this, and what we'll be left with is I going from 1 to n, EI1 times EI1 dot plus EI2 times EI2 dot plus phi I times phi I dot. We can substitute the values of all of these errors substituting the values of all of the error terms and simplifying it a little bit, we can show that this is, less than or equal to V dot is less than equal to minus of K1 E I1 squared minus K2 plus K3 divided by 2 times pi I squared minus K3 by 2 times E I2 squared. Thus, we see that our V dot is less than or equal to 0. Not only that, we can say a few more things. We can see that V dot is in fact negative definite. It is only equal to 0 when all of the errors are equal to 0. Hence, we say that V dot is negative definite. Thus, our system reaches the equilibrium. All the errors go to 0, which implies that formation is achieved. This was a very simple example of formation control setup where we showed that using a Lyapunov-based framework, so we use the Lyapunov to design the proof of it, but the control laws depend on the error terms. And using these simple error terms, we can show that we can actually use, or we can actually ensure that formation is achieved. Now, let us get into yet another application, that is rendezvous. The rendezvous problem. So what is the rendezvous problem? In these kinds of problems, we want all of the agents to meet at the same point eventually. Like the X positions and the Y positions of all of the robots must be the same. Again, as before, let us consider a unicycle setup and let us add a few more constraints to the unicycle. The constraints being that we want the linear speeds to lie between the range -1 to 1 and the angular speeds as well to lie between -1 to 1. We define a few terms here. Let me first show a figure that we are already familiar with. This is our alpha I, this is Vi, and this is Xi and Yi. Then we have the normalized velocity vector being equal to some term Ri given by cos alpha I and sin alpha I. Similar to this, we can define a normalized lateral velocity vector. We call it as Si. Si is equal to minus of sin alpha I and cos of alpha I. So again, the directions of SI and RI are this way. Let us now state, when do we say the two agents achieve rendezvous? We say that let Pi and Pj be the position vectors of robots I and j. Then, if the norm of Pi minus Pj is less than or equal to some number epsilon, where epsilon is very close to 0. Let's write it here. Then, so if the distance between the two robots is less than or equal to the small number epsilon, only then we say that robots I and j have merged or met or have met. Okay. So as soon as we achieve this bound, we stop the process, because then we know that all the agents have achieved, or the robots have achieved rendezvous. So let us consider in the underlying framework that the graph that we have is an undirected connected graph. Again, we can borrow the figure from here and use it later in this part. Okay. We see that G is connected. Further, we define a few angles. We define an angle phi j I. What is that angle? It is the angle between robot I. Sorry, Ri represents this distance. So it's the angle between Ri and the unit vector Pi of, let's say, Pj minus Pi divided by its norm. This makes it a unit vector. So it is the angle between, let's mark the I plus 1th vector here. And we can connect it with this dotted line. So this is J. So phi I is the angle between Ri and this. Let us also mark the angle of this vector. It is Pj minus Pi. So it will be given in this direction. Then the angle phi I is measured from Ri, meaning let us change this slightly, just for our ease of understanding. Let me represent it here. Yes. Now we can easily define phi ji. Phi ji, is this angle measured from Ri to this unit vector. This is phi j I. Let's highlight it in a different color. So let us also mention that it is measured from Ri. Then the following relation will hold. The relation being that cos of phi j I and sine of phi j I is equal to cos theta I sine theta I minus sine theta I and cos theta I. Multiplied by the vector pj minus pi. So this is a unit vector, so we divide it by its norm. We get this unit vector. So we can see that phi ij satisfies this relation, where this is nothing but a rotation matrix. Sorry, instead of theta, we have the angles alpha. With this, now we are ready to define a distributed control law. Let's write it. The distributed rule for rendezvous is given by this. One divided by the number of neighbors. So please note that this rule is for the ith robot. We take the summation here of j, pairing again of the neighbors of I, times cos phi j I and sine phi j I. Note that phi can be defined for all of the neighbors of robot I. Hence, this is a distributed rule, and we sum up these values for all of the robots and compute what is the we sum up the values for all of the robots which serve as neighbors of I, and using that we compute both Vi and omega I. This is also a bearing-based rule. So these results have been proposed in the paper. Let's highlight it. Rendezvous of unicycles bearings only and perimeter shortening approach. So in this paper, the authors are Zeng and D. Sun proposed the guidance law given here. And this guidance law ensures rendezvous. Let's write the key result. Agents are guaranteed to achieve rendezvous. And again, how can we prove that the agents will indeed achieve rendezvous? So the authors in the paper have also proposed a Lyapunov function. The Lyapunov function is V. To avoid confusion with the linear speed, let's write it as a V in this manner. Let's take the Lyapunov given as here, J summed over all of the neighbors of I times all of the inter-agent distances. Effectively, this is like summing up the perimeter of formed by joining all of the robots. Suppose these are the robot positions. Then this is one of the norms. This is another norm. So effectively, we are looking at the perimeter of the area in some way. If we assume a ring-connected set of unicycles, then we are only looking at the perimeter. So here we assume that, suppose it is a cyclic interconnection. This is the Lyapunov that they have proposed, and they show that the Lyapunov is indeed V dot is less than or equal to V dot is less than or equal to minus summation of the number of agents that, the number of neighbors that the ith agent has, and this summation is over I, where I varies from 1 to n. And this is equal to small vi squared, which we see is less than or equal to 0. And we can invoke the Lassalle's invariance principle and show that the largest invariant set consists of only the state of rendezvous, wherein, so let's write it, the set given by Pi equals Pj such that, Pi equals Pj for every I comma j. This set is the largest invariant set. And thus, with this, our job is done. Because we know from Lassalle's invariance principle that the trajectories will move towards the largest invariant set, which is nothing but the state of rendezvous. Hence, using the proposed rule shown here, rendezvous of agents is actually guaranteed. So far, we have discussed two different distributed control laws. The students are requested now to simulate these in MATLAB and vary the parameters and see the different behaviors that can be achieved using these two distributed guidance laws. Students can also try various other frameworks. For example, we have used a connected graph in this example. Can we extend this rule to a weakly connected graph and ensure rendezvous for the agents in that case? That could be one of the extensions. Yet another framework could be, in the case of formation control, we assume that the agents did not have any constraint of input saturation. Input saturation is expressed in this manner. Let me take you here. We see that Vi and omega I take actually bounded values. So this is one form in which input saturation can be expressed. Would the guidance law proposed for the case of formation control work if we now impose constraints of input saturation? So students can try out all these variants and modify the guidance laws or distributed control laws accordingly. With this, we will move on to the next step. Look at coupled oscillators. Kuramoto coupled oscillators. Kuramoto oscillators were first introduced by, let's write it, first introduced by Yoshiki Kuramoto in 1970s. And it has now become a cornerstone in various topics like network science, complex systems, and even in nonlinear dynamics. So let's start by quickly defining what is an oscillator. An oscillator is simply a system that shows repetitive periodic variation over time. Some examples would be a pendulum, an LC circuit, a quartz crystal, etc. So what is a Kuramoto oscillator? In a Kuramoto oscillator, we ignore the amplitude. Let's write it. In such an oscillator, we ignore the amplitude and focus only on the phase of oscillation. Hence we say each oscillator I has a phase theta I of t, which is given by, this is the main equation, theta I of t is equal to omega I times t plus some coupling terms. What is omega I? Omega I is simply the natural frequency of the oscillator. Let's write it. This is the natural frequency. It tells us how fast the oscillator oscillates on its own. And coupling effects, they tell us how other oscillators influence a given oscillator. How other oscillators influence it. So what did we say? We said that in a Kuramoto oscillator, we completely ignore the amplitude and focus on the oscillation. What do we mean by that? We mean that every oscillator is simply a system with a phase angle that rotates on a circle. So meaning the amplitude remains fixed, and what varies is simply the phase of the oscillation. And it can be drawn like this. If this is the phase theta, then we say that in a Kuramoto oscillator, we only worry about how the phase varies, and we say that the amplitude of it remains fixed. Meaning the dynamic model of the kinematic model, that's right. Since it is not really, that's right, it need not oscillate physically, so we won't call it a kinematic model, but we can say that the basic dynamical model is given by this. Theta I dot is equal to omega I plus some capital K, which is the coupling strength, divided by N, which is the total number of oscillators in the network, times the summation, J varying from 1 to N sine of theta J, minus theta I, where K is the coupling term, N is the number of oscillators. Okay. If this is our model, then we can clearly see that every oscillator communicates with every other oscillator in the network, which implies that G, which is the communication graph, is all-to-all connected, meaning a complete graph. A complete graph. So what exactly are we interested in? We are interested in seeing whether the phases of these oscillators get synchronized or not under this given model. So this is our dynamical model. Under this model, do the oscillators synchronize the phases or not? In order to understand that, we define something that we call as the order parameter. What is the order parameter? The order parameter is a very useful term. We define it as R e to the power I psi, which is equal to 1 by n times j going from 1 to n, e raised to the power I theta j. So what is the significance of the term R? Let's see. Significance of R. R equals 1 implies complete phase synchronization. How? If all of the phases become the same, so basically the question is, when does R become equal to 1? It can only become equal to 1 when all of the phases here add up or are effectively the same. So then the summation simply becomes r e to the power I psi is equal to 1 by n times n into e to the power I. Some, let's say all of the values are equal and they're synchronized at n bar. So this is the only condition when r becomes equal to 1. And this can only happen when all of the thetas are equal to some value theta bar, meaning the phases are synchronized. Similarly, r equals 0 only when the phases are distributed. The phase vectors, we can say, or the phases, simply put, are distributed uniformly on the circle or uniformly on the unit circle. Just for ease of analysis, we assume that the circle that we showed here has a radius of 1. It's a unit circle. Moving forward, so this term, which is the order parameter, how does the order parameter factor into the dynamical system? Let's see that. R e raised to the power I psi is simply equal to 1 by n times summation of e raised to the power I theta j, where I values from 1 to n. Let us multiply e to the power minus I theta I on both sides. 1 by n into summation I going from 1 to n, e raised to the power I theta j multiplied by e raised to the power I theta I, but minus of this. So on the LHS, we have r times e raised to the power j into psi minus theta I, which is equal to 1 by n summation of I going from 1 to n, e to the power I theta j minus theta I. Remember that both of the terms here are complex numbers. Let us equate the imaginary parts. It gives us r, so the LHS becomes r sine of psi minus theta I is equal to 1 by n summation I going from 1 to n sine of theta j minus theta I. And where is this term used? This is used in our dynamical system. So our dynamical system model is now equal to theta I dot, which was given by omega I, plus k by n summation of I going from 1 to n sine of theta j minus theta I. Now, notice that this entire part can be replaced with this. So what we are left with is, this implies theta I dot is equal to omega I plus k times r sine psi minus theta I. So basically, instead of thinking that the oscillator interacts with every other oscillator in the network, we can now think that the oscillator I interacts only with some mean field, which is modeled through this term psi. So let's sum it up. The oscillator I interacts with, or rather, interacts only with the mean field represented or factoring in through the term psi. What are some natural behaviors that arise in these Kuramoto oscillators? The natural behaviors that arise first is something that we already discussed, is R equals 0. When R equals 0, then we see that there is no global pattern. Let us now look at the interesting case of partial synchronization. Partial synchronization occurs when R lies strictly between 0 to 1. In this case, several interesting behaviors can happen. So we'll not give a proof of these results in this discussion, but the students are encouraged to read further on this. So we say that, let's say, when the coupling strength K exceeds a critical threshold KCR, let's say, then sometimes some of the oscillators get phase locked. This is the technical term to say that their phases get synchronized, while others continue to drift. So this is some of the behaviors that happens when there's partial phase synchronization. And something that we discussed earlier was full synchronization. Full synchronization simply gives R equals 1 and theta I equals theta j for every I comma j. Meaning the oscillators, let's write it, the oscillators are perfectly coherent and move as one. So this is how, or this is broadly speaking, a summary of how we study Kuramoto oscillators and what are the different behaviors that will arise out of them. With this, we'll end our discussion on Kuramoto oscillators and move on to the next interesting topic of cyber physical systems. Cyber physical systems. It is basically an integration of physical components with, say, computational algorithms. And sensors to control or perhaps monitor or let's write designed to control or monitor designed to control or monitor some physical processes in real time. This is what is a cyber-physical system. Some examples of cyber-physical systems would be smart grids and autonomous vehicles, healthcare monitoring systems, systems, etc. So these are cyber-physical systems. So cyber-physical systems are often characterized by several features, such as reactive computation, network connectivity, real-time operation, robustness, and safety-critical applications. Now, generally, in today's times, these systems are fundamental to advancements in various industries, including manufacturing, healthcare, energy, and transportation. Say, for example, hence, it is very important for us to learn how to effectively manage and control these systems. However, most of the times, cyber physical systems encounter certain risks, which are risks generally pertaining to their security. So in today's lecture, we'll briefly focus on this aspect of cyber physical systems. Security risks in cyber physical systems. There could be many kinds of security risks. To list a few, one kind of security risks could be software-based attacks. So what are the software-based attacks? So in these kind of attacks, the attackers often take advantage of the firmware or control software vulnerabilities. The firmware or control software. Vulnerabilities. An example of this is something that's known as DOS attacks or denial of service attacks. This is something we'll discuss in today's lecture. Yet another kind of attack would be a hardware-based attack. So in these kind of attacks, attackers often exploit weaknesses in physical components. In physical components like sensors, USBs, etc., or some manufacturing defects or design flaws and things like that. Basically, anything that pertains to the hardware aspect of the system. Yet another kind could be a side channel attack. So in these kind of attacks, attackers use physical signals like power consumption. Let's write it. Attackers use physical signals like power consumption or electromagnetic signals, electromagnetic signals, electromagnetic emissions, say, to extract sensitive data. There are some other kinds of attacks as well, like insider threats and physical damages. Basically, there are many kinds of risks, security risks associated with any cyber physical system. The particular risk that we'll discuss today is that of denial of service. Let me just mention the other ones. The other ones are physical attacks or, say, insider threats. So again, we're just mentioning these terms here. Students are encouraged to read more about them by themselves. What we look at is denial of service attack. And what could be the possible ways in which one can handle such attacks? Denial of service attack. So denial of service attack is simply an interruption in the communication channel. Interruption in communication, basically. So what does or how does this interruption in communication affect the system? What we are looking at is a regular system. Let's say we are looking at a linear system modeled as this. This system, when it faces a denial of service attack, it could basically mean interruptions of communication in various channels. First channel could be the measurement sensor to controller And the other could be the controller to actuator channels. So let's highlight it here. So interruptions in the sensor clusters, sensor to controller channel. And the other one could similarly be the controller to actuator. So it means that at certain points of time, let's say if it is controller to actuator, then there's a delay in which the actuator actually receives the input from the controller in the case of a denial of service attack. Similarly, the sensor, which is supposed to pass on the information to a controller, it does it in a delayed manner when it is under an attack. So basically, such interruptions, we can say, they actually, let's highlight it, DOS attacks hamper or impact the timeliness of information exchange. By causing packet losses. How do they do that? They can send a radio interference or a jamming signal, etc. By causing packet losses. How? Through radio interference or jamming. So this is how a DOS attack manifests itself for any given system. Meaning, effectively, data cannot be sent or received during these attacks, to put it simply. So what are the proposed solutions that one can adopt? So this is a very active area of research, and people have been working on various aspects of securities associated with cyber-physical systems. Some of the key proposed solutions could be updating the control action frequently enough whenever communication is possible. Let's mention it. So in this lecture, we're giving a very generic discussion on this topic. However, as I mentioned, there are rigorous works which express all of these constraints very mathematically and propose mathematically rigorous solutions. I will add a few references towards the end of the lecture, and students are requested to take a look at them if they're interested in this topic. So for now, let me simply write that one of the key proposed solution strategies could be simply to update the control action frequently enough. Frequently enough. So this way, there's a chance of losing less and less packets of data. Along with it, what must also be ensured is that the DOS jamming or the DOS attack, let's say, it should not occupy too large a fraction of time on an average. Must not occupy a or too large fraction of time. Effectively, by ensuring these two simple rules, one can more or less ensure that whatever is the desired behavior, if the desired behavior is that our linear system must remain stable even when it is under an attack, then it is mandatory that our attack must not prolong for a rather long time. And furthermore, when this step is ensured, only after that we can effectively design the control actions such that we can still operate in the time window when we are not under attack in such a manner that stability can be guaranteed. Students are directed to this paper. Resilient control under denial of service, by the authors. Students are directed to both this paper and the references therein to get more information on the topic of cyber-physical systems, and in particular to the security threat arising out of DOS attacks, and how exactly we can still ensure that stability can be guaranteed. With this, we move to the last application of today, which is the topic of opinion dynamics. In the era of opinion dynamics, it is basically the study of how opinions of individuals connected over a social network evolve over time. So the idea being that groups of people talk to each other and they discuss some topic, and later and over the time we study how the opinions of people evolve over time, and the changes in the opinions actually brought about by the continuous interactions with their neighbors. So do all of the agents always agree when they are talking to each other? The answer to that is no. Yet another behavior that occurs in social networks is polarization. Polarization can be described using two things. First, a signed network. In a signed network, the edges are allowed to have both positive and negative signs. Where positive sign means that two agents are actually friendly with each other, and a negative sign means that they are antagonistic towards each other. So this is a bit more realistic formulation where we also consider antagonism along with cooperation. And the rule that can be used to model polarization in a society is the opposing Laplacian rule, and it is helpful in the case of signed networks. In the opposing Laplacian rule, we primarily focus on something that's known as a structurally balanced network. So what is a structurally balanced network? Let us consider any social network perhaps given in this. Rather than drawing one whole social network, what we would rather do is consider two different subgroups. The vertices lying in the first subgroup, let it be V1, and the ones lying in the second subgroup be V2. If the network is structurally balanced, then we say that all of the interactions within a subgroup are actually positive in nature, meaning if I now number them 1, 2, 3, 4, 5, then in the adjacency matrix, the entry A 3, 5 is greater than 0. In fact, every Aij is greater than 0 if I, j both belong to the same bipartition, or they can belong to V2. Both. The same thing holds for this case. Furthermore, not only this, we also say that now there are two different groups of people, such that within the group people like each other. However, the people from different groups they have antagonistic feelings towards each other. Meaning, all of these H weights have negative signs, whereas all of these H weights have positive signs. If the society is divided into groups like this, then we say that the underlying network that gets formed is structurally balanced. So what often happens in these networks is that the people within one group, let's say this group, let us try to model polarization. The people within this group suppose they have some extreme opinion modeled by some value A. So this is the opinion of the first subgroup. Then the opinion of the second subgroup is always equal to minus A at steady state. This is what polarization looks like. So how can we model polarization? In order to do it in a continuous time frame, we proposed a Laplacian-like framework where we call it the opposing Laplacian L0, and L0 is simply equal to this. Let's say the ijth entry of L0. It is equal to the ijth entry of the standard Laplacian when I is not equal to j. The only change that happens is in the diagonal terms. The diagonal terms I are simply the summation of the absolute values of the off diagonal terms, where j varies from 1 to n. Just to give an example, let us construct a small network.
Is this network structurally balanced? The answer is yes, because we can divide this network again into two factions. 1 and 2 are cooperative with each other, and they're both antagonistic towards 3. What would this modified Laplacian look like? It would take the following values. Let's first write the standard Laplacian. The standard Laplacian is equal to this. If we look at node number 1, the diagonal entry, notice here, has become equal to 0 because it is the sum of the weights of all the outgoing edges. And the second term is -1, and the third term is +1. For node number 2, again, this is 0, and this is +1, and this again is -1. Similarly, for node number 3, it is in fact equal to -2. And both the entries are positive. So this. Notice that there are slight differences that occur in the structure of the standard Laplacian in the presence of antagonistic interactions. One such example can be viewed here. We see that the Laplacian is no more diagonally dominant. Hence, the nice spectral properties which which the standard Laplacian had, all those properties get lost if the network becomes signed. In order to counter this, we now propose the modified rule where we take the absolute values of the off-diagonal entries and make that equal to the diagonal entry. Hence, this becomes 2, then this remains -1, +1, -1, 2, +1, and this is +1, +1, and 2. So this is the opposing Laplacian rule, and the modified flow is -L0x. Then, when is it guaranteed that this model leads to a polarized behavior? When the underlying undirected graph is connected. So this is just one of the properties or one of the areas in which people work. In the area of opinion dynamics, there are a vast number of other areas as well, pertaining to different kinds of models, like the Hexagon-Krauss model, the Phyken-Johnson model, and the biased assimilation model, and so on and so forth. And there are several other areas, broadly speaking, in the area of multi-agent systems as well, where the tools that we have learned can be applied. So with this, I'll end today's lecture, and I hope that you've all become slightly interested in this area now, slightly more than what you used to be, and I hope that you'll pursue it further. Thank you.